My dear students, welcome to Goa classes. Today's chapter is number system for class 9. It is a very important chapter. So let me start the number system. Number system specially deals with the real numbers only here. So we should discuss the real numbers here in the class. So real numbers are the numbers that we often use in our daily life for counting, for measuring, for calculating. So these are the purposes for the real numbers. Next we go to the types of the real numbers. As we know that counting is very important for our daily use, so it starts with the natural numbers. These natural numbers are counting numbers as 1, 2, 3, 4. Next comes the whole numbers. Whole numbers, it adds 0 to the natural numbers. So in the set of the natural numbers, one 0 has come. As you see that it starts from 0 and it ends with all the natural numbers in the set. So that is the whole numbers. Next comes the integers. Now the integers, it comes into play because of the negative numbers of the natural numbers. So that way integers includes the natural numbers, the 0 and the negatives of the natural numbers. The set looks like this: -4, -3, -2, -1, 0, and the positive side of the integers. These are positive integers and these are negative integers, and in between there is 0. So this makes the set of integers. Now we come across rational numbers. These rational numbers are numbers that can be expressed in P by Q form. As P and Q are integers, that P can be 0 and Q is never equal to 0. This has to be remembered, that P can be 0 but Q is never equal to 0. And these P and Q are always integers. That is important for the identification of a rational number. These rational numbers include the fractions and the integers as well, as for example -4, -3 by 2, 0, 2 and 5 by 7 and so on. It also includes the terminating decimals as 0.5, 1.5. It can be expressed as rational numbers. You can see 1.5 is equal to 3 by 2 and 0.5 is equal to 1 by 2. Again comes the repeating decimals. These repeating decimals are 0.33, which can be expressed as rational number as 1 by 3. 0.111, each also can be written as 1 by 9. So these are all the range of the rational numbers. Next comes the irrational numbers. These are the numbers that cannot be expressed in P by Q form. So what it includes? It includes √3, √2. These are nothing but the square root of all non-perfect squares. Because 2, 3 are not perfect square numbers, so square root of these numbers are irrational ones. Another form of irrational numbers are non-terminating and non-repeating decimals as pi. 3.48350129, it continues indefinitely. So these are all non-terminating and non-repeating decimals. So these also comes under the irrational numbers. Hence, we find that real number is nothing but it consists of rational as well as irrational numbers. Now, as you see the number line, so more precisely, it is a real number line because it represents all real numbers only with 0 at the center, positive numbers on the right side and negative numbers on the left side. So 0 at the center and the positive numbers on the right side of the 0 and negative numbers on the left side of the 0. These all the real numbers only. This can be rational, this can be irrational also, right? So one of the important property of the rational number is that it increases as we move to the right. You see that while going to the right, it increases. 3 is more than 2, 4 is more than 3, like that. And on the negative part, we see that minus 1 is greater than minus 2, minus 2 is greater than minus 4.5, like that. While going to the left, it increases. It decreases rather, minus 4.5 is lesser than minus 2. You see, minus 4.5 is less than 3, minus 2 is less than minus 1 and 1 is less than 4. So, while going on the right, it increases, while going on the left, it decreases throughout the number line. Now, it is a very important part that while dealing the real numbers, we need the decimal expansion of the real numbers. This decimal expansion of real numbers can be like this way, that it can be represented in the decimal form as rational numbers, often written as P by Q. On dividing P by Q, we get while the remainder is 0, means we get the terminating decimals as 2 by 5, you find equal to 0.4. 14 by 5 is equal to 2.8, like that. Means it terminates after the decimal, it ends. Second is, remainder is 0, not 0. Rather, it repeats after a definite period. So, it gives non-terminating and repeating decimals. As we find 1 by 3. If we divide 1 by 3, we will get the result 0.333. It continues indefinitely. So, it is a repeating. 3 is repeating, but it is non-terminating. So, it is a non-terminating but repeating decimal. 1 by 11. It also, if we divide by 11, we get 0.09, 0909. So, here 09 is repeating. So, it is a type of repeating decimals, non-terminating. Next comes the irrational numbers. Now, these irrational numbers are represented in the decimal form as non-terminating and non-repeating decimals. As 0.2, just 0 as root 2 is equal to 1.414213 continues, and root 3 is equal to 1.732058 and continues indefinitely. So these are the numbers which are irrational, and it looks as non-terminating and non-repeating decimals. So we have learned that decimals of real numbers can be like two parts. One is terminating one, another is non-terminating decimal. Again, this non-terminating has two parts. One is repeating, another is non-repeating. So, what we have found that these terminating and repeating decimals are rational numbers, while non-terminating and non-repeating decimals are irrational ones. So, this gives clear demarcation between the rational numbers and the irrational one. This is very useful. You can remember it for your future references that terminating and repeating are rational and non-terminating and non-repeating are irrational. Now, we often come across of converting a decimal to a fraction. Now, what we do? These are the stepwise given over here. The step 1, we often write down the decimal divided by 1. In the next step, we multiply both top and bottom by 10 for every number after decimal. That is very important. That for every number after decimal. Suppose after decimal there are 3 numbers. So it will be multiplied and divided by 10 to the power 3 like that. So the power of 10 will be as per the count of the numbers after decimal point. Next step is simplify. Now we can take an example to explain it, that convert 3.625 to fraction. Now 3.625 divided by 1, then we multiply. We see after decimal point there are 3 digits, 6 to 5. So we will multiply it by 10 3 times over in the denominator as well as on the numerator. So after simplification, we find that it is equal to 29 by 8. So converting 3.6 to 5, it comes to 29 by 8. Now the converting a repeating decimal to a fraction. Consider a repeating decimal 8.373737 like that. So what we do? We will put x equal to 8.3737 or 37 like that, because here 37 is repeating. So number of digits repeating is 2. Number of digits repeating is 2 because 3 and 7 both are repeating here. Hence, as the number of digits repeating is 2, so we will multiply both sides by 10 to the power 2. So what we will get? If we multiply both sides by 10 to the power 2, we will get 100x equal to 8.3737 into 100, which will come to 837.37 and 37. So it will be marked as equation 2, whereas we have assumed as x equal to, this is our equation 1. Now we will do 2 minus 1, that is 100x minus x on the left hand side, and on the right hand side we get 837.37 minus 8.37 and 37. So what we will get? We will get 99x equal to 829. Then x comes 829 by 99. So my fraction is 829 divided by 99, which is equal to the repeating decimal of 8.373737 and like. And so this way we can convert a repeating decimal to a fraction. Now in the chapter, often we find that we are asked to find the rational numbers between two given rational numbers. As we have seen in the number line, that the number line consists of the real numbers. So in between two rational numbers, there may be infinite rational numbers. So there are some cases where we need to find the rational numbers between two given rational numbers. These two rational numbers, that is the start and end of two numbers in the number line. And case 1, we find that two end rational numbers are integers. Suppose we need to find 15 rational numbers between 4 and 5. So we need to find in between 4 and 5. What we will do? First we multiply both 4 and 5. That is our end numbers. 4 and 5 is the limit between which we need to find the rational numbers. Suppose on the number line it is 4 and it is 5. We need to find 15 rational numbers in between 4 and 5. Like that. So what we will do? We will multiply both 4 and 5 by 15 plus 1 and it will divide by 15 plus 1, that is by 16 by 16. So what we will get? 4 into 16 divided by 16, and on the right hand side 5 into 16 by 16. So we will get the end points as 64 by 16 and other end is 80 by 16. So what we will find? We can write as many natural numbers, as many rational numbers in between 64 by 16 to 80 by 16. We can simply increase the numbers as 64, 65, 66, 67 or like that, keeping the denominator 16. So we find 15 rational numbers in between 64 and 80. We can get it easily, very easily. So this is the case of finding the rational numbers between two integers when the end point is integer, that is 4 and 5. But suppose the end point is not an integer, is a fraction. So the end numbers, two end numbers are fractions. What we will do in that case? Suppose we are asked to find 10 rational numbers between minus 1 by 2 and 3 by 5. So what we will do? We say that here they are not integers, rather they have some numerators as well as denominators. So these denominators are here we find are different, that is 2 and 5. So what we will do? We will take the LCM. As we know, to make the denominator same, we must take the LCM of the denominators. That LCM is 2 of 5 is 10. So we will convert to same denominator as minus 5 by 10 and 6 by 10. Now we need to insert 10 rational numbers between minus 5 by 10 and 6 by 10, because minus 1 by 2 becomes minus 5 by 10 and another end limit 3 by 5 becomes 6 by 10. So we can write the rational numbers in between the two easily, as we see that minus 5 by 10, after that write minus 4 by 10, minus 3 by 10, minus 2 by 10, minus 1 by 10 and so on. We can on the right hand side also write 1 by 10, 2 by 10, 3 by 10 and so on. So these are the method to write the rational numbers between the two end numbers which are fractions. So we have learned to insert the rational numbers in between either end numbers are integers or the end numbers are fractions. So these are the two cases of inserting the rational numbers between two rational numbers. Now this is a special case that so far we have learned that we can insert as many rational numbers in between two rational numbers. Either the end numbers are rational integers or it is fractions. But another case is there that we should find the rational number between two irrational numbers. That is, end numbers are irrational. So how will you do? Suppose we are asked to find 5 rational numbers between root 2 and root 3. So we know the value of root 2 is 1.4142 and continues, and root 3 equal to 1.732 and it continues. We have learned rather, that terminating decimals are rational numbers. So this concept we can use over here, and we can find as many terminating decimals lying between 1.4142 and 1.732. So that will give the rational numbers between root 2 and root 3. So we find that such numbers can be 1.43, 1.45, 1.51, all are terminating decimals. Means these are rational numbers. So these terminating decimals can be the rational numbers in between two irrational numbers. So these are the way to find the rational numbers between two irrational numbers. Now, what is an irrational number? So far we have listened many words like irrational numbers. Now, what is the irrational number? If a root cannot be simplified to a rational number, then it is called a surd or irrational number. Another name of irrational number is surd. For example, 2, 3, 7 root 5. These are all surds because their square rooting of these numbers will not give any rational result. So these are irrational numbers and they are also called surds. Now suppose we are asked root 16. Root 16 is nothing but equal to 4. So it is not a surd. It is not a surd because it results to a rational number. Root 16 is 4. While these numbers are not resulting to any rational number. So these are irrational numbers or called surd. Now surds can be two types. One other is like surd, another is unlike surd. Now what is like surd? As we see, they have the same irrational part. For example, root 2, 3 root 2, 5 root 2. These are all like surd because their irrational part is their root 2. You can see that this having the root 2 part as the irrational one. So these are all like surds. Whereas unlike surds will be, they have different irrational parts. Suppose 3 root 2, 4 root 3. Here irrational part is root 2. Whereas 4 root 3 has the irrational part is root 3. So these are all unlike surds. Now we need to carry out some operations on surd because these are real numbers. So there will be some operations like multiplication, addition, all operations are carried out on the surds also, like the rational numbers. Now what is the operations on surd? Suppose addition. So in addition there is a rule that only like surds can be added. Suppose 2 root 3 and 5 root 3. We see over here both have the same irrational part, root 3 and root 3. So what we will do? We will simply add the integer 1, 2 plus 5 integer part, 7, and root 3 part will be common, so it will come to 7 root 3. So having the same irrational part, the irrational numbers can be added. But if the irrational part is different one, suppose 2 root 3 and 5 root 2, in that case we cannot add because these have different irrational parts. So further simplification is not possible over here. So this is the case of unlike surds addition. Same rule holds good for the subtraction also. Only like surds can subtract. For example, 6 root 2 minus 2 root 2. Both having the root 2 as the irrational parts. So these are like surds. So these can be subtracted as well. Like 6 minus 2 root 2, that is 4 root 2. Again, on the same rule of addition 1, that unlike surd 6 root 2 minus 5 root 2, further simplification is not possible. Now, after the operation on the surds, we come across that simplification of the surds. It is very important that we need to simplify the surds. Suppose it can be illustrated with an example. It will be easier for you to understand it. Suppose simplify root over 90. So what we will do? We will first break 90 into its prime factors. All of you know how to break into prime factors. So we get the prime factors of 90 as 2, 3, 3 and 5. So what we will do? We will simply write the prime factors numbers of 90. That is 2 into 3 into 3 into 5. Now in the next step, we will count the numbers which are in pairs. Suppose 3. It is 3 is in pair. 2 has no pair and 5 has no pair. So what we will do? We will take out the numbers which are in pair. Suppose it is 3 in pair. So 1 3 will come outside the square root. And rest of the numbers which are not having pairs will remain in the under square root. So 3 will be outside and 2 and 5 will be under square root. So it will come to 3 under root 10. So it is the value of the root 90. That is in a simplified form of square root of 90. It is an irrational also. It is an irrational also. But it is a simplified form of under root 90. So in the same way, if we are asked to simplify under root, a square root of 108, what we will do? Again in the same process, breaking 108 into the prime factors, we get as 2, 2, 3, 3 and 3. We will write down all the prime factors, 2 into 2 into 3 into 3 and 3. What we will get here? We find that 2 has a pair and 3 has a pair. So 1 2 will come outside and 1 3 will come outside. But 1 3 is a lone number which has no pair. It will remain under the square root. So what we find? The result is 6 root 3. So value of under root 108, if simplified, it will come to 6 root 3. So these are the process of simplification of a surd to a simpler form. It is the simpler form. These simpler forms are required while simplifying the expressions given. So this is very important to identify the numbers, how to simplify in this process.